Hello students, this is Mr. Ezra. Today we are going to talk about logarithmic functions. We're going to talk about characteristics of these functions, transformations of these functions, how to graph logarithmic functions. And you should feel like this is a little bit familiar to you because the last two videos have been doing the same thing with exponential functions. And exponential functions and logarithmic functions are inverses of each other. In other words, the x and y values have been swapped to get a new resulting function, and this new resulting function, all of the characteristics are gonna feel the same, except the stuff that was corresponding with x before is now going to correspond with y. The stuff that was part of the range before is going to be part of the domain now. Hopefully you'll see what I say as we dig in and get started. So before we dig into characteristics and transformations, we're going to look at a few of these kind of already worked out and just talk about them, and then we'll dig in a little bit deeper. So the basic parent function, I guess, that you might say, of log base 4 of x is going to look like this right here. Now, if you could turn this screen sideways, like you could rotate it, you might think this looks kind of like an exponential function because it is the inverse of an exponential function. So it's going to look like an exponential function kind of on its side, I guess you could say. In order to graph this, we would need to, in our graphing calculator, plot the log base 4 of x. Now, if you have a newer calculator and you're able to do the log base command under math, you can put it in the way that it looks here. But if you have an older operating system like I do, you're going to have to use change of base, which means your calculator, to get this graph, you're going to have to do log of x divided by log of 4. And this is what the graph looks like. So the calculator sometimes has a hard time when the function gets so close to the asymptote that it can't distinguish it from the asymptote. And sometimes you'll notice that the function will just stop kind of in midair and not continue to go down. In other cases, you'll notice that it'll put a line in for the asymptote to help you realize that that asymptote is there. But you need to know that these functions always go up or down forever. So it's gonna hug and technically get closer and closer and closer to the asymptote, and that they're always gonna go right and left forever. So there is an asymptote. It's not crossed. It is a vertical asymptote. And we just need to be aware of that and be okay with it as we graph these. Because of that asymptote, when we get our list of values, we will notice that some of the x values will correspond to errors in our calculator. And that's just because the function does not exist, in this case, to the left of the asymptote. At 0, which is our asymptote, this function starts to exist. It starts to have x values, and they will go forever to the right. Now, when you get your list from your calculator, so you'll see that 1, 0 is on there, and you can graph that 1, 0. 4, 1 is on there. You can graph that pretty easily. You can even graph 3, 0.8-ish by going, almost all the way up to 1. To get a little bit more detail, another thing that you want to do is to get your calculator out. And I'll actually pull this up so that you can see it. Here's what we see here. What we want to do is we want to hit the trace button and tell it to give us a point that's a little bit closer to the asymptote, like 0.5 is negative 0.5, or maybe 0.25 is negative 1. And what this allows us to do is it just allows us to get a point that is a little bit closer to the asymptote, so that when we're graphing it, we know that we are going in the right direction, that the curve is looking the way that it should. So use the values from your table, but add one more point somewhere between the x value in your table that is the smallest and the next number over, which represents your asymptote. With these types of functions, the domain is not all real numbers because we have nothing on the left of the asymptote. We start x values from 0 to the right forever, not including the 0. So our domain is going to be from 0 to infinity. The range is all real numbers because we have an arrow down and an arrow up, and every single possible y value is a potential y value on this function. I should point out that this is kind of the opposite of what we saw with the exponential function, where the domain was all real numbers and the range was limited by the asymptote. The asymptote for a parent function, meaning there's no shifts left or right from the regular position of the logarithmic function, the asymptote is going to be x equals 0. And if we have a shift left or right, we'll see that that asymptote will move with the function. This function is always increasing. It's just not, it doesn't have an x value forever, so it's going to be increasing along the domain from 0 to positive infinity. It crosses the x-axis at positive 1 comma 0, but because of the asymptote, it does not cross the y-axis. For end behavior, you're going to have to think left in, right in. On the left end, what x am I approaching? Well, I'm approaching an x value of 0 for the asymptote. So as that x value approaches 0, as it goes to the left towards 0, the y values go down forever towards negative infinity. On the right side of the function, as I travel along to the right, I'm forever going to the right, which is positive infinity, and forever going up, which is also positive infinity. So I gotta think left in, right in, what's happening to y. Remember, f of x is another way to write y. So this is kind of a way to describe what's happening at the ends. Another example of a parent function, but this one has a 1/3 as the base instead of a 4. What we notice with the 4, which is a number bigger than 1, is that the function is increasing. It's going up. And when we have a number that is between 0 and 1 as our base, the function is decreasing. It's going down. So that is kind of a pattern that you'll see unless there's some sort of reflection across the x-axis or y-axis. In this function, we graph it using y equals. And again, I have to use change of base, so I said log of x divided by log of 1 divided by 3. I didn't mention this in the last graph, but I want to set the window of my calculator to be the same as the graph that I'm given. So since I'm going from -4 to +4 on the x-axis and y-axis, I changed my x-min and y-min and x-max and y-max to be -4 and +4. I wanted to see what it looked like, make sure that I was graphing it correctly, and I do see that my graph seems to match the one that is there. And then I got some x values to use and some y values to use, some points to put on the graph. So 1 comma 0 and 3 comma -1 were very easy points for me to add to this graph. I then needed to use that trace command that I told you a minute ago. Go back to the graph, hit the trace button, and type like 0.5. And it'll tell you that the y value that goes with 0.5 is about 0.63, and I estimated about where that was, about halfway, a little bit more than halfway up. And then I drew my connect the dots through all of those dots with arrows on both ends. Now, as far as the characteristics go, my domain is still 0 to infinity. That's all the possibilities for x, because I have no negative values for x on this graph. So they all start at 0. I do have a range from negative infinity to positive infinity. Now, this is a sticking point for some students. These intervals should always be from least to greatest. So it doesn't matter that the function is going up or down. I'm thinking my y values that are possibilities for y values on this function have possible y values from negative infinity, which is forever down, to positive infinity, which are forever up. It should always be in order from least to greatest. The asymptote is going to be x equals 0. Because we don't shift left or right. That is where the parent function's asymptote is going to end up being. This function is decreasing along the domain from 0 to infinity. It crosses the x-axis at 1 comma 0. There is no y-intercept. And for end behavior, again, we have to think left and right. So my left one on the left, my x's get closer and closer and closer to 0, while my y's go up, up, up towards positive infinity. On the right side, my x's go right, right, right towards infinity, and my y values go down, down, down towards negative infinity, and you just have to get used to thinking and writing it that way. You'll notice again that all of these domains, ranges, intercepts, asymptotes, they are all kind of like opposites of what we saw when we were looking at the parent functions of exponential functions, because all of the x values and y values have swapped places. These domains and ranges and asymptotes are going to, essentially the x values and y values are going to change places. Now let's dig in a little bit deeper into the transformations that you'll see. So I guess you could say that all the transformations, we could use letters to represent them. So really we've got some y equals a log, and it doesn't matter what the base of the log is, so I didn't even put anything there. And We might have a number in front of the log, which could impact the graph. We might have a number inside the logarithm that is in front of the x, and if there is addition or subtraction, there's parentheses even inside the log to separate that b out, and it has some impact. We might have x plus or minus inside the logarithm. That has an impact on the graph. And then if we have plus or minus at the end, that's going to have some type of impact on the graph. So the number at the very front, if a is negative, we will see what's called a reflection, and it's going to be a reflection up or down across the x-axis. If b is negative, if the number that's a coefficient inside the logarithm is negative, then that's going to be a reflection over the y-axis. So that would be left to right reflecting across the vertical line, which is the y-axis. Shifts left and right happen inside the logarithm with x plus or minus a number, and you always have to think it's the opposite of what you see. And any plus or minus at the end is going to indicate a shift up or down. And I hope by now that this is starting to feel familiar to you, because these are the same types of transformations that we've seen over and over again. Now, I want to point out that A and B can also describe stretches and shrinks. In other words, vertical stretches, vertical shrinks, horizontal stretches, horizontal shrinks, but we're just not going to include those today. We're not going to worry about them at the minute. It does happen. It is part of it. We're just going to kind of ignore that. So let's look at a few of these transformations down here. I've already done the first few, and then we'll do the next few together. In example 1, because the plus 2 is inside the logarithm, we have to think the opposite of what we see. So instead, the plus 2 is going to indicate a shift to the left 2. And if you were to graph this function, you would see that shift to the left 2 from what usually has an asymptote of 0. It's now going to shift to the left. If we have plus 5 at the end after the logarithm, so the logarithm has ended, we've got the parentheses, and then we're adding 5, that's when we're going to see a shift up 5. Example number 3 has two transformations. It has a negative at the front, which indicates a reflection over the x-axis. And there is also a minus 1 after the x inside the logarithm, which is a shift left or right. Because it's minus, we got to think opposite of what we see, so that's going to be to the right 1. In number 4, we see two transformations. This negative inside is going to impact the function and the plus 3, but we have to be a little careful here, because the shift left or right is not going to be based on what you see here if there's a negative at the front. What we have to do is we have to factor out that negative, divide it out of the negative x and the plus 3, and what's left behind after we do that will give us our two transformations. The negative is going to be a reflection across the y-axis, and the minus 3 after the x is going to be a shift to the right 3. This one sometimes trips students up because they want to say left 3 when they just look here, but if there's a negative in front of the x, we have to factor it out first, then decide how we're going to transform with the shifting left and right. In example 5, we see three transformations. We have this negative at the very front, which we by now hopefully are seeing that that's a reflection, and it's going to reflect across the x-axis. We see x plus 2 inside the logarithm, so that is going to be a shift to the left, since it's always the opposite of what we see in there. The opposite because the basic function that we're using is minus h. So to get x minus something to give us positive 2 would have to be minus negative 2, and that would cause it to shift to the left. I hope that kind of makes sense. And finally, at the very end, we have the minus 7, so that's going to be a shift down 7. In number 6, there is a negative inside in front of the x. In this case, there's no plus or minus, so I don't have to worry about factoring anything else. I can just indicate that that is a reflection across which axis? That's right, since it's inside, it's a reflection across the y-axis. And then the minus 4 is going to be a shift. It's outside of the logarithm, not a part of it, so it's going to be a shift down 4. So hopefully you'll get to these practice questions, and this will make sense. You'll be able to do this pretty easily, especially seeing as we've done it recently with other types of functions. We do want to talk about the vertical asymptote here. The asymptote for logarithmic functions is always a vertical asymptote, which means that when we describe this line, we've got to describe it as x equals a number. And that number that we get is going to be affected by the horizontal shifts left to right. So when we're looking at those transformations left to right, it tells us what our vertical asymptote is. If I shift left 2, my asymptote is x equals -2. If I don't shift left to right, it's going to stay at x equals 0. If I shift right 1, it's going to be at +1, x equals +1. You do need the x equals because it describes the vertical line, and you do need the number because it describes where that vertical line crosses the x-axis. In example number 4, just like we said a minute ago, since this is -x plus 3, we have to factor out or divide out that negative to give us x minus 3. That lets us know that there is a shift right 3, so the asymptote would be x equals +3. In example 5, because it's a shift left 2, it's going to be x equals -2. And in example 6, since there's no plus or minus inside the logarithm, it's going to stay at x equals 0. The last thing that we want to discuss is the domain, the range, and the end behavior. And you should again notice that these are similar to those exponential functions, but the x's and y's have switched places, which cause the domain and the range to switch places as well. So the domain of exponential functions is all real numbers. Now that's the range of this type of function, a logarithmic function. The range of exponential functions was impacted by the asymptote. In a logarithmic function, it's the domain that is impacted by the asymptote. So it's you have two choices for the domain, but the range is always the same for logarithmic functions. The end behavior, as we saw, is going to be real similar, but the x's and y's are going to change. So we'll have to think left and right and just be real careful when we do those. Now let's look at 2 more examples before we close out this video where we have at least done a little bit of a transformation. Remember to put this in your calculator. If you don't have the log base button, what you have to do is use change of base in your calculator. Log of x plus 2 divided by log of 3. Your calculator will give you a graph that you can look at and you can trace to get points, and you can also go to the table to get some points. Now, transformations, I usually pull from this before I graph it because I want to see if the transformations on the graph match up with what I think should happen. When I look at the x plus 2 in this one, I see a shift left 2. And on the graph, I see that shift left 2. So instead of starting at the y-axis, it's starting over here at left 2. So it's coming up, from down here forever to the right over here. Now, 3 of these points, I can get a few of them here, but remember, I'm going to hit the trace button on my calculator to get another one of those points. So I need to get at least 3 points graphed. So to get an extra point, I'm going to go to my graphing calculator, hit trace, and choose a point that is somewhere between -1 as an x value and -2. So maybe -1.5 would give me a little bit of extra information. And I can include that -1.5 comma -0.63 as one of the graph points that I graph. -1.5 comma -0.63. I'll then grab 2 easy to graph ones, -1 comma 0 and 1 comma 1. Of course, I have the ability to get even more detail than just these 3 points, but this will be a good starting point for me. -1.5 comma -0.63 is about right here. -1 comma 0, 1 comma 1. I can see 4 comma 1.6 about right here. And now I've got this idea of where the graph is coming. Now, my asymptote is impacted by this shift left too. So I know that it is going to be x equals -2. So I'm going to need a dashed line on -2 to represent that asymptote. And then when I start sketching in my curve, I want to hug that and start peeling away from the asymptote to go to the right forever. So something like this, it's kind of curving out to the right. Domain is impacted by the asymptote, so it starts at -2. There's nothing to the left of -2 and then goes forever to the right. The range is all real numbers, and you can write the symbol for all real numbers if you'd like to, that are with the 2 lines on it, or you can use interval notation from -infinity to +infinity. This function is always increasing along the domain, and the domain is -2 to infinity. So I can tell the interval that it's increasing. It's always increasing from negative to infinity. There's an x-intercept of -1. And the y-intercept I'm going to get from my table, since it does cross the y-axis this time. In the two previous examples, it has not. But because of the shift left, it crosses the y-axis, and it crosses right here at 0, 0.63-ish. So 0, 0.63 will be a good estimate of where it crosses that axis. For end behavior, as I go left on this function, I'm getting closer and closer to the asymptote of -2. And as I get closer and closer to the asymptote of -2, my y values go down forever towards negative infinity. On the right side, as my x values go forever to the right towards positive infinity, my y values are forever going up towards positive infinity as well. So I have to think what's happening at the ends. This is right towards positive and up towards positive. The left is not towards negative infinity though, because it's stopped by the asymptote, and I have to represent that in the problem here. Last example, we've got the log base 2 of x plus 3 minus 1. There are two transformations here. There's a shift left 3 and a shift down 1. Now the shift down 1 will cause the function to shift down, but it's not going to impact the asymptote or anything. It's really that shift to the left 3 that's going to impact the asymptote. In fact, our new asymptote is going to be x equals -3. So at -3 on the x-axis, I can go ahead and put that dashed line because I know that's where the asymptote is. Now you can see on the graph that seems to be the case here. We go -1, 2, 3, and this function doesn't cross that invisible asymptote. Your graph isn't usually going to show it, but some calculators do show the asymptote. And even in the table to the left of when you get to the asymptote of -3, you start seeing errors. We see -2, -1, -1, 0, 0, 0.58, 1, 1, 2, 1.3, 3, 1.5. So we really have enough detail here. I should trace the graph as well to see where it crosses down here to get a better idea. But I am just going to kind of peel this off like this to get my function graph. So the 3 points that I got were all from the table there. Domain, I have nothing to the left of the asymptote, so it's going to start at the asymptote and go forever to the right, but the range is all real numbers. I should point out that if the function is reflected across the y-axis, then the entire function would be on the left side of the asymptote, and we would go from negative infinity to the asymptote for our domain. So you do want to look at the graph and not just assume it's going to be the asymptote comma infinity. That's not always the case. This function is always increasing along the domain, so I can go ahead and add that interval in. There is an x-intercept in this one of -1, 0, and there is also a y-intercept from this one of 0, 0.58-ish. The end behavior on the left end, we are, as x approaches the asymptote, the y values are going down towards negative infinity. On the right side, as x goes forever to the right, the y values go forever up. We've got our end behavior. I want to get the calculator out and show you one more thing. So that is it for this example. And what I want to do is kind of go back to this guy right here. What if it didn't cross at like a perfect place that showed up in my table, and I had to find that 0 with my calculator? Just to remind you of how to do that, you want to hit second, calc, and you want to choose the second choice, which is called 0, because remember 0 is another kind of term for where it crosses the x-axis. It's where the function has a value of 0. So I hit enter for a left boundary that is on the left side of where it crosses. Then I go to the right across it, and I hit enter for a right boundary on the right side of where it crosses. So it should say, do you want me to guess between here and here what the 0 is? And I'm going to say yes by hitting enter, and on the bottom of the screen it's going to give me the 0. Now, sometimes your calculator will put y equals 0, and for some reason, sometimes it will give you a number that is super close to 0. Like this would be negative 0.13 zeros before you get to 9, 1. It's essentially 0, and that's okay. What we want to see is that it crosses at an x value of -1. That's what we're going to get from here. So if your calculator doesn't get from you, you can always calculate it using your calculator if it's not in the table. Well, that is it for today. We've talked about logarithmic functions, how to graph them, characteristics, transformations. Try to get through it as quickly as possible, but if you have any questions that are not answered in the notes, please ask them in class.